Good morning and good afternoon, everyone. Welcome to today's RiskOn webinar. Today, we have the privilege of diving into a topic of critical importance and relevance, investigating the role of climate change and development on hurricane compound hazard across a spatial scale. We honor to have with us an esteemed expert, our colleague, Dr. Avantika Gori. Dr. Gori recently joined the Department of Civil and Environmental Engineering at Rice University as an assistant professor. Dr. Gori received her PhD from Civil and Environmental Engineering Department of Princeton University. During her career, she received multiple awards, including a Geohazard Section Award for her graduate research, as well as National Defense Science and Engineering Graduate Fellowship, and also USGS Scholarship for Water Resource Research. Without further ado, I will pass this to Avi to talk about her exciting research with us. So Avi, the floor is yours.
Perfect. Thank you so much for that really nice introduction. So hi, everyone. As Mona mentioned, my name is Avantika Gori. I'm an assistant professor at Rice University, and today I'm going to talk a little bit about some of my recent work on investigating the role of climate change and development on hurricane hazards and risk across different spatial scales, so at the regional and at the local level. So to motivate this talk, I'm sure many of you know that tropical cyclones severely threaten coastlines across the globe due to their extreme winds, storm surges, and intense rainfall. And particularly in the North Atlantic, the Gulf and East Coast of the US are highly vulnerable to the impact of different tropical cyclone hazards. So one motivating example that I like to use is the case of Hurricane Ian, which made landfall in Fort Myers, Florida in 2022. So Hurricane Ian made landfall with extreme winds with peak wind gusts up to 140 miles per hour that caused widespread structural damage to homes and properties in Fort Myers, which you can see on this image. Hurricane Ian also generated up to 15 feet of storm surge in the Fort Myers beach area. And in addition to causing widespread coastal flooding, this also caused infrastructure damage, such as bridge unseating, which you can see here in the second image. And finally, Hurricane Ian caused over 20 inches of rainfall in some portions of Central Florida. And this resulted in widespread inland and urban flooding that resulted in significant property damage and evacuation of some communities. So I think this is a really good example to illustrate why we need to think about all three of the hazards induced by tropical cyclones, since their combination can often cause damage that exceeds the damage from any single hazard alone. So climate change may increase the severity of these coastal hazards. So there's a growing body of literature that climate change will result in an increase in tropical cyclone intensity. So if we have more intense tropical cyclones, what does that mean for our coastal hazards? Well, of course, we'll have higher wind speeds. In addition, we may have increasing peak storm surge. So the image here shows a projection of increased storm surge at Galveston, Texas, due to climate change. And we may have also more intense and higher duration rainfall events. So the image here shows a shift in the rainfall distribution from the blue, which is the historical climate, to the red, which is one possible future projection by the end of the century. So as we can see, all three of the hazards may increase in the future due to climate change. Climate change and socioeconomic development may also drive increases in TC damage or losses in the future. So some previous work looked at the role of both changes in storm intensity and socioeconomic development to quantify potential changes in TC risk, which they calculate as expected annual damage. And we can see that according to the study, the climate change is expected to result in about a 100% increase in TC risk by the end of the century. Similarly, population growth and wealth increases are projected to result in about an 80% increase in risk. So both climate change and socioeconomic development have been shown to have potentially comparable magnitudes of impact on overall TC risk. The limitation with existing work is that these studies typically only consider the effects of wind hazard. So these risk models don't explicitly account for changes in rainfall or changes in storm surge. And so they may actually not tell us the full picture about how TC risk could change in the future. So now moving kind of from the regional risk quantification to the local level, when tropical cyclone rainfall and storm surges co-occur in coastal regions, they can exacerbate overall flooding. So here I'm kind of showing two different schematics. So when we have a tropical cyclone making landfall, it will often generate high storm surges that propagate toward the coast. At the same time, we may have intense rainfall inland that tries to drain out toward the coast. And the combination of the rainfall runoff and the storm surge often increase the overall flood levels, resulting in a compound flood. So here you can kind of see another schematic where the surge wave and the rainfall wave interact, and you have this increase in flooding, which is the orange. So a big question is, how will the combination of projected changes in storm climatology, sea level rise, and urbanization impact these compound flood dynamics? So of course, if we have changes in increases in rainfall resulting from tropical cyclone change, that would increase this rainfall runoff wave. If we have, sea level increasing the base ocean level upon which storm surges act, then that would increase the surge wave. And similarly, if we have widespread inland urbanization that converts large areas of natural land, which can absorb water and slow down water, into concrete areas that don't absorb water and increase the speed of drainage. So the effect of urbanization at local scales may also exacerbate flooding by increasing rainfall runoff. So we want to investigate how these dynamics all come together to impact local flooding. So first, I'm going to talk about this idea of regional tropical cyclone risk assessment. So since the historical record of tropical cyclone occurrences is relatively sparse, we don't have enough historical data to give us a good picture of what is the risk to coastal communities. So instead, we rely on physics-based models to simulate a very large set of synthetic tropical cyclones. So these tropical cyclones didn't actually occur, but they're physically realistic given a certain climate state. So we can start with output from global general circulation models or reanalysis. This will tell us features of the large scale climate. And then we can use a statistical deterministic model, which I'll cover in a little bit more detail later, to generate thousands of synthetic tropical cyclone tracks. We then utilize physics-based models to simulate each of the hazards. So here, this wind model is a fully physics-based wind model. We use a simplified physical rainfall model to simulate the convective rainfall in the tropical cyclone vortex, and a hydrodynamic model called ADCIRC to simulate the storm surges at the coast. So if we simulate hazards from all of these thousands and thousands of events and include things like sea level rise projections, we can understand the joint hazards affecting a certain coastal county. We then trained a pretty simple statistical damage model that takes as input the county level GDP, as well as the county level hazards that we modeled, and we can predict the damage from each storm. And then we can get the probability distribution of damage and an estimate of the tropical cyclone risk. So I'll very quickly cover the synthetic track model. So here we use large-scale climatologies from the reanalysis or GCM data, and we randomly seed vortices within these large-scale environmental fields that move through a simple beta advection track model and a simplified deterministic intensity model. So these synthetic tracks on their own are often biased compared to the true historical climatology. They're based on models, so of course they're not a perfect representation of the true climatology of TCs. So we then implemented a sampling-based approach so that we can resample all the tropical cyclone tracks, and we can correct the distribution of the intensity so that we match better the historical climate. And then we can apply that bias correction to look at future climatologies. So we have, a bias corrected future projection. So the rainfall model is a very simple convective rainfall model, and it basically relates the precipitation rate in the TC vortex to several different components that result in upward velocity or convection. So these components are frictional convergence effects, topographic effects, vortex stretching, baroclinic or kind of shear effects, and then radiative cooling. And although this model is relatively simple, when we use it across thousands of storms, it gives us a pretty good understanding of the risk of rainfall at a certain location. And here are just some comparisons from a previous study showing that compared to a higher fidelity regional climate model, this simple model can reproduce the spatial distribution of rainfall well. Finally, I'll just mention the hydrodynamic model. So this is the advanced circulation model. Here I'm showing the mesh that we use to simulate the storm surges. So we apply the tropical cyclone wind and pressure fields. We simulate them in this finite element shallow water model, including tidal forcing, and then we can get relatively high resolution estimates of the storm surges along the coastline. So this model goes down to 1 kilometer coastal resolution. So now I'll talk a bit about how we trained the statistical damage model. So we first trained the model using a pretty large data set of observed county level TC damages. So this data set comes from the NOAA storm reports, and it's from 1996 to present. And we collected all of the county level TC damages. So first, we kind of just investigated aspects of this historical database. And what we see is that some regions have a higher frequency of damage and kind of follows our intuition. So the Gulf of Mexico really stands out as having a high frequency of damage because we have a lot of tropical cyclones here. Also, the coast of North Carolina has a high frequency of damage because many storms track parallel to the East Coast and affect North Carolina. When we look at annualized damage, so this is basically the average damage per year in the historical record, we see that, of course, the Gulf of Mexico and North Carolina pop out as hotspots, but we also have the Northeast popping out, and this is mainly driven by the extreme damages from Hurricane Sandy. So whereas some places are more vulnerable because of high frequency of hazard, other places are more vulnerable because of high exposure. So we have a lot of assets concentrated in the Northeast. We then looked at how different hazards are correlated with damage. So what you can see is looking at the correlations between storm tide and damage, rainfall and damage, and wind and damage, all of them are significantly correlated. And no one hazard is really predicting the vast majority of the variance of damage. So this tells us that we really need to consider all three hazards explicitly if we want to capture a good picture of the overall damage. So then we trained this very simple regression model. We have two versions. One is for inland counties. So here, the log of the damage is a function of the log of the peak wind speed occurring over the county, the total rainfall, and the log of the county GDP. For coastal counties, we have basically the same structure, except for we also have the log of the peak storm tide. So it's accounting for the storm surge effect. And just training these two simple regression models, we can actually reproduce the pattern of observed damages pretty well. So on this scatter plot, I'm showing for all storms producing at least $1 million of damage, the log of the observed damage on the x-axis and the model damage on the y-axis. And we see a pretty good correlation of 0.8 between the model and the observations. And similarly, if we look at the spatial pattern of damage, we can see, for example, Hurricane Irene, that the spatial footprint of damage and locations of high damage are pretty well correlated between the model and the observations. So although this is a very simple statistical model, because we have a good high resolution specification of the hazards, we're able to get a realistic understanding of the damage. So now we can use this model to look at TC risk using that big data set of synthetic tropical cyclones. So here I'm showing for the historical climate from 1980 to 2005, what we estimate is the expected annual damage from tropical cyclones. And then for comparison, we have the observed annualized damage just from 1996 to 2020. And what we see is that although they match in some ways, so the general spatial pattern is consistent where we have high damage in the Gulf of Mexico, and then also along like the eastern seaboard, we do see that this is much more spatially diffuse, let's say, whereas here we have, not really a complete picture because we have very limited tropical cyclone landfall. So this map is really driven by random chance of where a tropical cyclone happened to hit in the past 30 years, 25 years. So this kind of shows the utility of using these large synthetic data sets to give us a more complete understanding of TC risk. If we then look at how projections of future climate change would impact our understanding of TC risk, here I'm showing a projection using the SSP to 4.5 scenario for the end of the century. And we see that the first image showing the percent increase in risk due to tropical cyclone climatology change. So we see pretty large increases in risk along the Gulf of Mexico, but the largest in the Northeast. And this is primarily driven by increasing rainfall in the Northeast that's driving a large increase in tropical cyclone damage. When we add in projections of sea level rise, we see that basically every coastal county lights up. So sea level rise is going to overwhelmingly drive the increase in some locations in terms of increasing TC risk. So now if we look at socioeconomic changes, so this would be population growth and wealth increases. So population growth projections show kind of a net migration to the southern states along the Gulf of Mexico, and consequently, they're causing an increase of up to 50% in damage. But this magnitude is relatively small compared to the increase in damage we would expect from wealth increases. So if we account for population growth and wealth increases, we would expect between 200 to 250% increase in risk. And so really the wealth increases are the main socioeconomic driver here of increasing risk in the future. And so finally, I will point out that projections of future TC risk are much larger when we explicitly consider all hazards versus when we just consider wind hazards. So what has been done before. So the first image is what I showed before. This is the projected increase in risk if we can explicitly consider rain, wind, and storm surge. And then on the image B is the increase in risk if we only consider wind. And here you can see that if we don't consider all of the hazards, we would have a much lower projection of increased risk. The main reason for this is that some increase of the tropical cyclone rainfall is correlated with the intensity, but some of it is not correlated with the intensity because a warmer world contains more water in the atmosphere, and so we're generating more rainfall that's not correlated with metrics of the tropical cyclone intensity. And so if we don't explicitly consider that in our risk framework, we may actually be underestimating how risk could change in the future. So this really highlights why it's important to consider all of the hazards explicitly in risk frameworks rather than relying on a single hazard alone. So now that I've talked a bit about this kind of regional understanding of patterns of risk, I'm going to switch gears a little bit to talk about really at the local level, what's going on in terms of compound flood dynamics between tropical cyclone rainfall and storm surges. Oh, I forgot I had a summary slide. Okay, I kind of summarized the main findings already. So yeah, again, like across the US, climate change and socioeconomic growth combine to cause large increases in damage. And it's really the increase of climatology and wealth increases that are the main components of this. We saw that historical losses are driven by all three hazards, so we can't just consider one hazard alone. And finally, this type of statistical damage model can really be helpful for us to understand large regional shifts in TC risk and regional patterns, but this is not suitable for local scale decision making where we would need a much higher resolution understanding of the hazard. So this brings me to the next topic, where I'm going to look more depth into the local compound flood dynamics of tropical cyclones. So here I'm focusing on the Cape Fear River in North Carolina, and I really want to understand how compound flood dynamics might change under future land use conditions and future climate change. And I'm focusing on one particular historical storm, which is Hurricane Florence. So Hurricane Florence made landfall in the Cape Fear estuary in 2018, and it was a really notable event because it caused both very high storm surge when it initially made landfall, but it also stalled over the study area for a few days and caused really large rainfall accumulations. So it's a very interesting extreme compound event to study. So to understand the flooding from Hurricane Florence and how it might change in the future, I use a physics-based inland flood model. So here I'm just showing the domain of this flood model. It's forced with the storm tides from that big AdCirc model that I presented before, as well as upstream river discharges, which are these red locations. And then I apply Hurricane Florence rainfall to this computational mesh. And this is also a 2D shallow water model. So it's basically resolving all of the main physical mechanisms of flooding occurring between the rainfall and the storm surge. So we had validated this model pretty extensively using several historical hurricanes. So you can see some different tracks of the hurricanes. We compared collected high water marks versus our modeled peak flood depths. We got pretty good performance. We also used a tidal gauge located in the study area to look at the time evolution of modeled versus observed flooding. And we can see that for a range of different events, this coupled model framework can produce pretty good estimates of flooding. So we want to use this model to run a sensitivity analysis to see how could flooding change in the future if we have future urbanization, if we have future TC climatology, and or if we have future sea level rise. So first, we needed some projections of plausible land use scenarios by the end of the century. Here we're using the Integrated Climate and Land Use Scenarios, ICLIS, which is from the EPA. And these land use projections follow the SSPs. So to be consistent with our climatology projections, we're using this SSP2 4.5 land use scenario. And what you see is that by the end of the century, we would have a large swaths of natural land potentially converted into residential or developed land. So in particular, grasslands and forests are projected to be converted to low and medium intensity development by the end of the century. So we want to understand, what effect is that conversion from natural land to developed land going to have on flooding? Similarly, based on those big regional projections of how tropical cyclones might change in the future, we can adjust the rainfall and storm surge hazards accordingly. So here I'm showing the joint distribution at this location between the rainfall intensity and the peak storm surge. And so here, this image is really just showing the joint probability distribution of those two drivers. And Hurricane Florence is here, this red star. So if we want to understand what a Florence-like event would look like by the end of the century, we can adjust the rainfall hazard and the storm surge hazard based on our big regional projections. And here the rainfall is really in terms of the climatology aspect, the rainfall will change by a lot more than the storm surge. So the storm surge actually has a negligible change, but when we add in sea level rise, so this blue is actually the sea level rise compared to the historical, which is black, then we see a really large increase because the sea level rise is really driving the increase of storm surge. So then we did this sensitivity assessment to see, okay, how is flooding going to change if we apply each of these change factors separately, and then if we apply all of them at once. So if we just apply land use changes, we see a relatively small impact on flooding in the main stem of the estuary, which is here. And that's because this is a very big river. So smaller changes in rainfall runoff are not going to have a huge impact on the water levels. But when we look at the smaller tributaries that flow into the Cape Fear River, that's when we start to see some significant impacts of increased water levels. If we just apply the climatology change, the vast majority of this is impacting the rainfall dominated regions. So that's because we're projecting a lot more rainfall in the future. And also portions of the upper estuary. So areas of red or dark maroon are having much larger increase in flood hazard. If we apply a medium sea level rise scenario, so this would be like the 50th percentile based on the IPCC 6 projections, we're seeing the main impact is occurring in the main stem of the river, where sea levels are propagating up this estuary to increase the flooding, and this gradually gets attenuated as we continue to move upstream. But if we account for all change factors together, we notice that we have a nonlinear increase in the middle portion of the estuary. So now the increase, if we sum up the increase here, here, and here, it's actually lower than what we get when we model them all together. And so this is really showing that we have nonlinear change in the flood dynamics due to the combination of all of these change factors. And so we can also look at how this would change the duration of flooding. So not just the peak of flooding, but the duration as well. So here I'm showing a couple different locations where I'm showing the full time history of water levels. So if we just focus on location 1, we can see that the base case is this one in black. And then the combination of all the change factors is in orange. And what you'll notice is that we have a very long duration of high flooding when we consider all of the change factors together. And another thing that's interesting is that in the existing observed case, we have the peak of the flooding driven by storm surge. So this first peak was the surge-driven flooding. But in the future, we will see a change in the flood regime. So now the peak water level is driven by this later peak, which is from the rainfall runoff. So not only are we seeing an increase in duration, but we're also seeing the flood regimes that are most important shifting in the future due to the combination of these different change factors. And so to summarize this kind of more holistically across the study area, we can look at how the different flood zones could change through time. So here red equals places where the rainfall is the dominant flood mechanism. Blue are areas where the surge or the tide is the dominant mechanism, and then the green are places where we have transition. So basically both rainfall and storm surge are important in driving the overall water levels. So if this is our observed kind of base case, the impact of land use change doesn't have a huge impact on changing these flood regimes, since it tends to be a smaller impact and mostly localized in the tributaries. The climatology change, so here we have a lot more rainfall occurring, and this shifts the transition zone downwards. So now we have more areas of rainfall dominance and the transition zone is shifting downstream. If we have sea level rise, then we have the opposite effect. So higher sea levels will push the transition zone upstream because tides are able to propagate further upstream in the tributary. But then if we in the estuary, but then if we consider all the change factors together, we actually see a big expansion in the transition zone. So now we're basically combining, let's say, the impacts of sea level and climatology, and we have a much larger portion of the study area that's vulnerable to this type of compound flooding. And so this really illustrates how climate change and tropical cyclone climatology change and sea level rise can work together to change the flood dynamics, basically, in estuary environments. So just some summaries from the study are that tropical cyclone climatology change, sea level rise, and urban growth increase both the flood severity and the flood duration. Flood dynamics in these estuary environments can be largely altered from the different effects of these flood drivers. In the Cape Fear region, we found that urban growth has a smaller impact on flooding than climate change, but this might not be true in other locations. So for example, some other large metropolitan areas like the Houston-Galveston area, in past studies, we've seen urbanization playing a much larger role than climate change in driving changes in flood hazard. So it's important to consider both of these aspects when we look at how flood dynamics may change in the future. So I'll end the webinar with just some conclusions across both of these studies. So changes in climate and coastal environment can drive changes in TC hazards that have impacts across different spatial scales. So this schematic kind of shows that we have two effects happening at very different scales that can propagate across scales. So here we have kind of going downward is decreasing spatial scale. So going from large spatial scales to small. So at the very largest spatial scales, we have changes in the global climate. So this is what's simulated by GCMs. These changes in the large scale climate will impact changes in the will cause changes in the tropical cyclone climatology. So that's the intensity of tropical cyclones, their movement, their tracks. And then changes in the tropical cyclone climatology also cause changes in the regional wind, rainfall, and storm surge hazard, as well as the dependence between those hazards. The change in the hazards then will cause changes in flooding depth and extent at very local scales, and also cause changes in the regional tropical cyclone damage, so those kind of risk projections that I showed. So simultaneously, while these changes in the climate are cascading to smaller scales, we have small scale changes in the coastal landscape that are propagating up. So if you think about, at very small scales, we have an individual house being built, a person moving to a new county. But those small scale changes eventually add up to cause significant impacts on flooding depth and extent, and fundamentally change the tropical cyclone risk due to changing the exposure of different counties. So we see these kind of two different change factors working simultaneously to change tropical cyclone risk across spatial scales. So with that, I will end my talk. I'm very happy to answer any questions, and thank you all for your attention.